to Organic Chemistry 1, and today we're going to talk about alkynes and their reactivity. Um, and so this is just a follow-up to the alkenes video, and let's jump right in. So what are we going to learn today? We're going to learn about how to make alkynes. We're going to talk about alkyne synthesis. We're going to talk about how to name alkynes, very short uh, tutorial on nomenclature. And then we're going to talk about the reactions that alkynes are able to do. Right, hydroboration, just like the reactions of alkenes, alkynes do a lot of the same reactions, but the results are a little bit different. So we're going to talk about hydroboration, oxidation, mercury sulfate, oxidation to carboxylic acids, um, reduction of alkynes into alkenes and alkanes, and then using terminal alkynes as nucleophiles or bases. So let's jump right in. How do you make alkynes? Well, first of all, if you look here, this is a alkyl dihalide, and so if you treat that with 2 equivalents or 2 moles of potassium hydroxide, right, you can get an alkyne from that via a double elimination, right? So what I have shown here is 1 mole of KOH, and this is the first elimination to give you the alkene, right? The vinyl bromide that you see here, and then that can undergo a second elimination using another mole of potassium hydroxide to give you the alkyne that you see here, right? So an alkyne is simply any compound that contains a triple bond, right? And so let's keep going. So let's talk about alkyne nomenclature, right? It's very simple. You follow the same IUPAC rules that you would follow for alkenes and alkanes, right? The suffix "-ine" that's indicative of a triple bond, and then the number in front of the name, which we're going to talk about in a second, is indicative of the location of the triple bond. So this particular molecule is 1-hexyne, right? So 1-hexyne, the 1 corresponds to the alkyne or the triple bond being between carbons 1 and 2, shown here. And then the hex corresponds to the fact that the chain has 6 carbons in it, and the "-ine" tells us that the chain has a triple bond in it, right? So 1-hexyne is the proper name for this molecule shown here. All right, so let's talk about some reactions of alkynes. And the first reaction we're going to talk about is hydroboration oxidation. You can see up top, if I treat this with BH3, right, and then follow that up with hydrogen peroxide. This is the same reaction that you learned for alkenes, right? But the outcome is a little bit different. You still get an alcohol, right? You still get anti-Markovnikov addition across the triple bond to put the alcohol on the least substituted carbon as shown here. But what's different here is that once you get the alcohol, you're left with what's called the enol form, which is shown here, right? That enol form is not stable. So what it does is it actually rearranges to give you what's called the keto form, which is shown over here to the right. All right. So anytime you do hydroboration oxidation of an alkyne, this is the outcome, right? Where you get an alcohol on the least substituted carbon, and then that enol rearranges to give you the keto form. And this is especially significant if you're doing this reaction on terminal alkynes. A terminal alkyne simply has the triple bond at the end of the chain, right? So if you remember from the reactions of alkenes, when you add BH3 to a multiple bond, the boron is going to add to the least substituted carbon, and the hydrogen, one of the hydrogens from the BH3 is going to add to the most substituted carbon to give you this intermediate shown here. I need to kind of give you a little bit of a caveat here. This is not actually what this looks like, right? Because if you remember from the reactions of alkenes, and if you haven't seen that video, you can go back and watch it. I'll put the link here. If you haven't seen that, right, that BH2 can add to 2 more alkynes, and so that'll give you an intermediate, which I'll show you in a minute, right? And so once I get to here, then I treat this with hydrogen peroxide, right? And when I do that, that's where my alcohol comes from. And again, I go through this mechanism in detail with alkenes in this video here where the link is shown. All right. And so this is the actual intermediate after you do the hydroboration step, the first step, right? Because there are 3 hydrogens on boron, that BH3 can add to 3 triple bonds to give you an intermediate that looks something like this. And then in the second step, it's just basically an insertion and then followed by elimination to give you the alcohol, right? So you get this enol, but the enol is unstable, right? And so what happens is it undergoes a process what we call tautomerism. So here's the enol, right? And if I do resonance on the enol, which is shown by these arrows here, right? I'm doing resonance. I'm putting a pi bond between carbon and oxygen, and I'm taking a pair of electrons from the pi bond that's here, and then I'm putting those electrons onto carbon, right? So I get this anion, right, after resonance. And then that actually does proton transfer in the next step, right, where the electrons on that carbon pull off the blue proton, and then the electrons in the OH bond go back to oxygen, right? So that's how I get my keto form. So I go from the enol to the keto form, and this keto enol tautomerism falls under the category of a rearrangement, right? And it rearranges through resonance, and it gives me the keto form, which is more stable, right? So when you look at the overall reaction of hydroboration oxidation, the final product is a carbonyl. It's not an alcohol. The alcohol is more of an intermediate than it is the final product. So it's a little bit different when you do hydroboration on an alkene, right? There's a little bit of a difference. All right. Same thing with the Mercury-catalyzed reaction. If you remember from the reactions of alkenes, mercury acetate followed by sodium borohydride gives you Markovnikov addition of H and OH across a double bond. So here you get Markovnikov addition still, but you get an enol, right? So the OH is now on the most substituted carbon, as you can see here, indicated right here, right? And then that again tautomerizes to give you the keto form. We're not going to go through the mechanism, but I do want to remind you that mercury adds in a Markovnikov fashion. So you remember from the alkene video, BAM and MEM, right? BAM is boron, is anti-Markovnikov. MEM is mercury, is Markovnikov. So it's a Markovnikov addition of H and OH across the triple bond. That's the kind of the essence of what's happening here. All right, another reaction is you can also convert alkynes into carboxylic acids. This is analogous to an ozonolysis, where you basically break the triple bond in half, and each carbon in the triple bond gets oxidized up to an acid, right? So you can see here are your 2 carbons here, and those 2 carbons, when I treat it with potassium permanganate, that triple bond breaks, and then each one of those 2 carbons gets oxidized up to the acid. And you can see that this carbon corresponds to the carbon on the inside of the triple bond, and then this carbon corresponds to the carbon that's on the outside of the triple bond.